Assalamualaikum warahmatullahi wabarakatuh and good morning. We are from group 4 and this is our assignment. Our assignment consists of this equation, which is GS equals to K over S times S plus 5 times S plus 15. And these are our questions. So for part A, we have number 1, sketch the root locus, and we will use a graph paper. Number 2, the breakaway and the break-in points of the root locus. Number 3, the j omega crossing points and the gain k at the j omega crossing points. Number 4, the range of gain k to make the system stable. Number 5, asymptotes. And number 6 is the line of damping ratio equals to 0.456. Since the equation consists of only denominator for the values, and for the numerator we don't have any values, we only have k. So for denominator, it represents the number for the poles. So for the poles, we have one pole, one root is equals to 0. The second root is equals to -5, and the third root is equals to -15. After we mark the roots at 0, -5 and -15, so we know that this is our root 1, this is our root 2, this is our root 3. Hence we know that the locus exists at the left of the odd root, so we choose root number 1 and root number 3. So to the left of root number 1, so we go like this. To the left of root number 3, we go like this, because we know that the locus starts with poles and end with 0. So if we start it with poles, then we know that the arrow will be going out. So since we know that the locus is going out from the poles, so since the poles here meet each other, pole meet with pole, so we have a breakaway point here. So we do like this. This is only an estimation. So we will move to the question number 2 to obtain our breakaway point.
Yeah.
For question number 2, which is to find the breakaway point, we have the formula here, summation of 1 over s plus zi. So we have
3.
So we have the summation of 1 over s plus number of zeros, and this is the summation of 1 over s plus number of poles. Since we don't have zero value, we only have poles value, so we substitute the values here. 1 over s plus 1 over s plus 5 plus 1 over s plus 15. So we combine all together. We expand the equation, and we have this. We have s squared plus 20s plus 75 plus s squared plus 15s plus s squared plus 5s equals to 0. So we have 3s squared plus 40s plus 75 equals to 0. And then when we factorize the equation, we have s plus 2.26 and s plus 11.08 equals to 0. So we have finally s equals to -2.26 and s equals to -11.08. From the graph, we know that our breakaway points is in between the range of 0 and -5. So we only accept this and reject this, since this is -2.26 and this is -11.08, which is out of the range between 0 and -5. Okay, since we accept the value of -2.26, so we do the finalized breakaway point. Okay, we have the arrows from the poles here from the right side and here from the left side. Okay, so our breakaway point is negative 2.26. We have like this.
3.
Since we know the crossing point at the real axis, we also should know the crossing point at the j omega axis. So for question number 3, we need to know the j omega crossing points and the gain k at the j omega crossing points. So we have here the equation for the closed loop system. This is the equation for the open loop system with unity feedback system. So for the closed loop system, we just move the k here and plus k here at the bottom. So we have here, finally we have k over s cubed plus 20s squared plus 75s plus k. So after we have the closed loop system, ts, we transfer it into the rules table. So we have here the rules table, s3, s2, s1 and s0. So we transfer this 1 and then 75 here, 20 here, k here. Okay, so we have here, and then we do all until s0. So we have here, in order to find the j omega crossing, we need to know the value of unknown k. So to obtain k, we assume that the odd number for the s, okay, since the k starts here from s2 and then continue to s1 and continue to s0, so we assume that the rows of 0 is here, the rows of zeros is here. So we take this equation out and then we equate it to 0 because this is, so we equate it to 0 because we assume that this system is marginally stable system. So if marginally stable system, we will later find out the j omega root for the system. So we equate it to 0 and then k, we get 1500. So we get k equals to 1500. We substitute the value of k into this. We take this as 2, so 20 as 2 plus k. So k is 1500, so equals to 0. And then we factorize it. We get s equals to plus minus square root of 75. So we have plus minus 8.66. 8.66. We have plus minus 8.66. So we know that the crossing point at the j omega axis is 8.66 here and negative 8.66 here. Okay, for question number 4, which is to find the range of gain k to make the system stable, we know if our system is stable, we have it larger than 0. So for the rules table, we have here k here and then we have k here also at the first column. So at the first column, we make it larger than 0, more than 0. So if we have more than 0 here, then we have k is less than 1500 and k is more than 0 for s equals to 0, so k is more than 0. So our range is, the range of k is between 0 and 1500.
3.
Okay, for question number 5,
3.
we need to find the asymptotes for the root locus for the system. Asymptote is important in order to obtain the location of the zeros in the system, because the zeros are not mentioned here. So the zeros are all in infinity location. So we have to find the angles for the location of zeros. Okay, so for the formula, we have here theta A equals to 2k plus 1 times 180 degrees over the difference between the poles and the zeros, where k equals to 0, 1, 2, 3 and so on. So we have here for number 1, for k equals to 1, theta A equals to this, and then we get 60 degrees. For k equals to 2,
3.
okay, this is k equals to 0. K equals to 0, we get 60 degrees. When k equals to 1, we have 180 degrees. For k equals to 2, we have 300 degrees. And for k equals to 3, we have here 420. So 420, we minus it with 360 degrees. So we get 60 degrees back. Since 60 degrees here is the same as this, so we don't need to continue these steps. So we know that the asymptotes for the system, we have 3. We have 60 degrees, we have 180 degrees, and also 300 degrees. Since we know all the asymptotes for the locus, okay, we need to know the points where the asymptotes will spread here at the real axis. So in order to find the points where the asymptotes spread, so we need to find it using the formula, and we have the formula is sigma A is equals to summation of finite poles minus summation of finite zeros over number of finite poles minus number of finite zeros. Okay, so since we only have poles, we know that the location of the poles are 0, 5 and negative 0, negative 5 and negative 15. So we substitute the values here, and we don't have any values for zeros. So, and the bottom one is finite poles, number of finite poles minus number of finite zeros. So we have 3 in difference, and hence the sigma A is equals to negative 6.67. So negative 6.67, we need to find the location here at the real axis. Okay, the point of sigma A is negative 6.67. So we know that our asymptote are 60 degrees, 180 degrees and 300 degrees. So we start from 60 degrees. Okay, so I've already marked the 60 degrees with protractor. So we just, okay, so we have here 60 degrees, and then for 180 degrees is for this pole, 180 degrees to the left, so it is infinity, and this is also goes to infinity. Same goes here to 30 degrees. So 30 degrees is from here to here. So we have here 60 degrees from here. Okay, so this big angle is 300 degrees. So we have already completed the asymptote line, and then we want to draw the root locus. Okay, so we have here the point of real axis and the point on the j omega axis. So we just make an arc. Okay, so we need to okay, that one is for the upper part, and the lower one is okay. So we have here the root locus done. The root locus is done. Okay, this is the line of the root locus. This line follows the line made by the asymptote line, because the asymptote line, the function of the asymptote line is to make sure that the line here is almost parallel to the asymptote line. So it is like a guidance for the root locus to go to the infinity. For question number We will find the line of damping ratio given that zeta is equals to 0.456. So we know that theta is equals to transverse of cos zeta, so equals to transverse of cos 0.456. Then we get theta is equals to 62.87. So this theta is represent this angle from here. So this is theta equals to 62.87. So we will sketch the line on the graph paper. So the line of the damping ratio zeta, okay, if we follow the angle is 62.87. So this is the line. So we will sketch the line up here. Then this is the angle of 62.87 degrees. Okay, so this is the line of the damping ratio is equal to 0.456, and the line here represents the omega R of the damping ratio. For part B, we need to design a controller that will reduce the settling time by a factor of 4. So the given situations are, number 1 is to specify the type of controller to be designed. Number 2 is for the uncomposited system, the K that should be used is 257.841 and closed loop poles at -1.809 plus minus J 3.531. For number 3, for the composited system, we should use K is equals to 256.819. Number 4 is to calculate the peak time and the steady state error for uncomposited system. And number 5 is to compare and discuss the results on uncomposited and composited systems. For question 1, the controller type is PD controller is because the question stated that we need to reduce the settling time by a factor of 4. So we don't focus on the steady state error. Instead, we focus on the reduce the settling time.
3.
For uncomposited system, from the root locus, the settling time can be calculated by this formula, which is 4 divided by omega n. So we know that our system for uncomposited has the poles at this on the real axis. So on the real axis is 1.809, so we substitute it and we get 2.21 second for the settling time for uncomposited system.
3.
For the composited system, we need to find the new settling time. Since the question asks for reducing the settling time by a factor of 4, so we need to divide the settling time of the uncomposited system by 4. So when we divide it, we get 0.55 seconds. This is for the composited system, the settling time for the composited system. After we find the settling time for the composited system, we can automatically find the real part and the imaginary part for the composited system. So in order to find the real part first, so we substitute the settling time, the new settling time, into this formula, which is 0.55 seconds equals to 4 over the real part, and we get the real part is equals to 7.236. Then for the imaginary part, we can use the formula. Then we should find the theta to find the angle here. Since we need to know the imaginary part for the composited system, so we should know the theta first. So theta is obtained by this trigonometry. So we know that our imaginary part is 3.531 and our real part is -1.809. So we can find theta by using tangent. So tangent theta is equals to 3.531 over 1.809, and our theta is 62.87 degrees. So from this theta, we substitute the theta here. So tangent 62.87 degrees is equals to omega d nu over 7.236. This value is equals to the new real part, which is for the composited system. So we get the imaginary part for the composited system is 14.124. Then we finalize it, the composited system, the poles are located at negative 7.236 plus minus J 14.124. The given equation is GS equals to K over S times S plus 5 times S plus 15. So from the equation, we plot the poles at 0, negative 5 and negative 15. So after we plot the the poles at the real axis, then we plot the real part and the imaginary part for the composited system, the new composited system. So we obtain it just now is the real part, we get negative 7.236 and the imaginary part is 14.124 plus minus. So after we plot the real part and the imaginary part, so we find the intersection between the two, and then after we find the intersection between the two, so we plot, we do a straight line from each of the poles. So from 0 we do a straight line here to the intersection. From negative 5 here we also do a straight line, and also the same as negative 15. So to find the angle for each of the angles here, theta, so we have here theta 1 for 0. So theta 1 here, since it is outside here, so we need to minus 180 minus the angle obtained here. 180 minus the angle obtained here to get the angle outside. So 180 minus, we do tangent is because by the trigonometry function, so we get minus transverse tangent 14.124 over 7.236. Okay, then we get here is 117.13 degrees. So the angle here is 117.13 degrees. So the second angle we obtain 99 degrees, and the third angle we obtain 61.2 degrees. To identify the zero location on the real axis, we need to sum the angles, and later on we need to substitute in this equation. So to obtain theta ZC, if we get the theta ZC, we could identify the zero location on the real axis on the graph paper. Then okay, so after we sum up all the angles, we get 277.2, and then we plus theta ZC equals to negative 180. So theta ZC we obtain 97.2 degrees. Using trigonometry, we could find the location of the ZC where the zero on the real axis located. Okay, so by using the trigonometry, we can see that the angle here is minus by 180 is because this is 97.2, so it is more than 90 degrees, so we minus it. Then we get 82.8, and then we get ZC is equals to 5.45. For the uncomposited system, the peak time is obtained by using this formula, which is pi over omega n square root of 1 minus z squared. is equals to pi over, this is equals to the imaginary part. So this is the old imaginary part, which is for the uncompensated system, and we get here is 0.89 second for the peak time.
3.
To make sure that the system is stable, we found out using the rules table, because there is no sign changes here, so the system is stable. Hence, the system is stable, only then we can find the steady state error of the system. Okay, to find the steady state error of the system, it's given that the equation, the k is given, which is 257.841. So we substitute the k into this kv, because later on this kv, we can find the steady state error by dividing 1 divided by kv. So this kv is obtained, and kv is 3.44. So the steady state error is 1 divided by 3.44. We get 0.291. 0.291 is for the steady state error for uncompensated system. For the compensated system, to find the peak time of the system, we use the same formula, which is pi over imaginary part, and our imaginary part for compensated system is the new imaginary part, which is 14.124, and then we get 0.22 seconds for the peak time.
Okay.
To make sure that the system is stable, we use the same method, which is by rules table. So after we find out, then there is no sign changes detected, so the system is stable, then only we can find the steady state error for the compensated system. So for the compensated system, we obtain the kv is equals to 3.42. Then our steady state error is 1 divided by 3.42. We get 0.292.
3.
So for the comparison between the two systems, which are the compensated system and uncompensated system, we found out that the peak time of the compensated system has been reduced to 0.22 seconds if we compare it with uncompensated system, which is 0.89 seconds. So the compensated system, the peak time has been reduced to 0.22 seconds. So we fulfill the question, and furthermore, for the steady state error for both system, we don't have like any difference, any big difference between them, only just a slight difference between these two, which is one is for compensated system, we get the steady state error of 0.292, and uncompensated system, we get the steady state error of 0.291. So there is no big changes for the steady state error, only for the peak time we have a big difference between compensated and uncompensated system. Thank you.